Welcome everybody on Zoom, welcome everybody in the lecture hall to this new lecture of Information Systems for Engineers. So we are now in the middle of a pretty tough and complex lecture on database design theory. The next one will be again, maybe a bit more practical. Before we start, I quickly recap a few things. We've looked into anomalies, the issues with bad design. I've told you this is good design, but we need to formalize what it means to be good design. So we defined the notion of the first normal form, which we saw at the beginning of the course with only atomic values, no nestedness. Then we looked into functional dependencies, which basically means that some columns in a table might be dependent on some other columns as a function. So this is called a functional dependency. So if you know some values, then you know some others. It's like a guessing game. We looked into superkeys, which are special kind of functional dependencies where the right-hand side is everything. So if you have a few attributes that, if you know them, tell you the entire tuple, then this is a superkey. Then we looked into minimal superkeys, because of course, if you have a superkey, every superset is also a superkey. So if you take the minimal ones in the sense of set inclusion, then you get candidate keys. In that example, for example, A, B, B, C, and AC are three candidate keys, but ABC is not. It's a super key, but it's not minimal. You can remove attributes and it's still a super key. Then we looked into actions in order to derive functional dependencies from other functional dependencies. So this is quite abstract, right? When you arrive at the level of the actions, it's really, here's a set of functional dependencies that apply to my table. You don't even look at the table anymore, just look at the functional dependencies. And then you try to play games by replacing them and finding equivalent ones, right? So we saw the transitivity rule, we saw the splitting rule, we saw the combining rule, which is the same the other way around, the splitting rule. Then we saw the reflexivity rule, that if you have a set of attributes, they functionally determines any subset of them. It's almost trivial if you think of it. The augmentation rule means that you can add something on both sides. And we saw, and here we are really entering the axiom and rules, which is a whole domain of logic and mathematics, which it turns out that three axioms are enough. So if you have reflexivity, augmentation, and transitivity, that's all you need in order to do all the derivations you want without looking at tables. That's the beauty of it. What does that mean? It means that these two, splitting and combining, you can actually prove out of the other three. And I encourage you to try to prove the splitting and combining rule using only these three. It's a very good exercise to try to take it as a mathematics puzzle. All right, so I have two questions for you now to check that you understood the material, and then we'll move on. So, here's the first one. I'm giving you four statements. They look alike. So a functional dependency holds for a table universe. Remember that that's all the intention of the designer of the table, like what do you want to see in the future of your universe. So a functional dependency holds for an entire universe if it holds for all tables in that universe. Then the same thing for a superkey, holds for a table universe if it holds for all tables in the table universe. Then the same thing for a candidate key. Candidate key holds for the entire universe if and only if it holds for every table in the universe. And a unique constraint, in the sense we saw in SQL, holds for a table universe when it holds for all tables in the table universe. All right, so multiple answers possible. Some of them are correct, some of them are incorrect, and you need to figure out which ones. Functional dependency, superkey, candidate key, unique constraints. So again, these statements can be true or false, and you need to figure out the ones that are correct. Let me give you a bit of help. Three of them are correct, and there's one of them that is actually incorrect. And you might remember that I gave you a warning about that last week. So this is something you should know. Let's look at your answers. Oh, wow, this is quite even, okay. Okay, let me give you the solution. The one that is incorrect is the candidate key. Super key, functional dependency, and unique constraints, it's equivalent. You can say it holds for the universe, or you can say it holds for every table in the universe. It's the same thing. A unique constraint, actually, it's just a special case of a super key, right? If you have a unique column, that basically means that column is a super key, right? Okay, but why the candidate key? Because remember that you might have accidental super keys. So it might be that if you look at the entire universe, most of the tables will be pretty random and will not have extra dependencies. But once in a while, you might suddenly be lucky. And for example, all the inventory numbers turn out to be distinct, pure luck. Then you end up with the column with the inventory number being a super key, but that's accidental. It's not by intent, right? The problem is that when that happens, it makes super keys no longer minimal. They would be minimal over the entire universe, but for that specific table where you have an accidental smaller super key, then a candidate key for the universe is not a candidate key for the specific table. That's the reason why you should try to avoid speaking of candidate keys for a specific table. Always talk about candidate keys as the designer, having in mind everything you want, right, for the candidate keys. In the exam, we'll always give you representative tables. We will avoid accidental dependencies because otherwise it just confuses for no reason, right? Okay, so that's the warning. Candidate keys, be careful because you might have accidental super keys, and then a candidate key for the universe might not be a candidate key for all tables. Here's another one. Take it as a game. Let's play a game. So I'm giving you an attribute set. Just to free you from notations, here I'm using uppercase for attributes. So all of these letters are attributes. And I'm giving you a set A. I dropped the curly braces, the quotes, and so on, because we kind of don't do that with functional dependencies. So we have one attribute. It's a singleton set with just A. And I'm giving you these dependencies. A gives you B, B gives you C and E, D gives you F, C gives you G, and H gives you F. Under these functional dependencies, which hold for, let's say, universe of table, what's the closure of the attribute set A? What is this game? Basically, it's like this. If I'm picking a tuple at random and I'm hiding it, I'm not telling you which tuple it is. And then I give you the value of A. What other columns can you give me the values of? That's the closure of attribute A. And you can use the functional dependencies in order to give me the closure. So if you know A, what else do you know? The answers coming in. That's a fun game, right? It's actually, once you get the hang of it, it's actually quite easy, right? Just turn into a habit and something quite mechanical to do. Yeah, slowing down. So let's see now what you say before giving you the answer. This is, you guys are amazing. You are amazing. Okay, so I'm pretty sure, okay, I trust you. I'm pretty sure it's the correct answer. Yes, it is the correct answer. How did you do that? Well, look, we start with A. The first dependency gives us B out of A, so we have A and B. B gives us C and E, so we have A, B, C, E. And C gives us G, so we have A, B, C, E, G. And then you're stuck. There's nothing else you can do. You don't have D, you don't have H, so yeah. A, B, C, E, G. Okay, congrats, I love that. Okay, everybody got it right. Okay, so now we are in a good condition then to continue with the slides. Just give some time for Zoom to load them, and there you go. So this I already did, and the 5 actions, the 3 that are actually enough. And now we continue with the notion of minimal basis. What is this? A minimal basis is basically a simplification. Imagine that I throw at you a big bag of functional dependencies and I ask you to clean that up. What does it mean? It means you need to find an equivalent set of functional dependency that doesn't have any redundancies or unnecessary things in there. You basically try to simplify, remove things, make it smaller, but it must be equivalent. You do not have the authorization to remove any constraint in there. It's just an equivalent one. So here's an example. With it's a bag of 3 functional dependencies. I'm again using now lowercase for the attributes, right? Again, I don't use the curly braces, the quotes, you know, technically I should, right? These are sets of attributes, sets of strings, but again, people don't do that. In fact, people even drop commas very often. They just write the letters without even bothering to write the commas. So don't be surprised if you see these compact things. Okay, so we want to clean that up because that looks a bit like a mess, right? So in Switzerland, we love to do that. So let's go ahead. So I copy that over. What can we do? First, I told you about the convention. With the splitting and combine rule, you have 2 conventions that people like. One convention basically splits everything. So you basically turn the first one, for example, into A gives you B, A gives you A gives you C, right? You split it. And then all the right-hand sides have a single attribute. This is one way to basically format things. The other one is the opposite. You group everything together that has the same left-hand side. There is no correct, incorrect. It's really just a matter of convention. For the purpose of this lecture right now, I'm going to take the convention that we love splitting things. I think in the exercises, you might see the other convention, but it's really a matter of taste, really. Okay, so is there anything useless in there? What can we throw away? Yes, maybe the microphone. Maybe we can. Yeah. So tell me.
A gives us A, it's useless.
Yep.
And if A gives us also C, B gives us C, is useless. So A gives us A and B gives C.
Yeah. Bonus questions. Can you give me the name of the 2 rules that you used in there? Because you use actually some of the actions. Even it's obvious, right? It's natural, but you use 2 actions. Yeah. Maybe on Zoom, somebody knows? On Zoom, maybe? Can you name the 2 rules that we've used here? Right? We remove AA and we remove AC. What did we use as the rules? Otherwise, I can tell you. AA, that's the reflexivity rule, right? It's the reflexivity rule that tells you that A gives you A is a trivial thing, just pops out of nowhere, so you can also remove it. It's equivalent. A gives you C is the transitivity, right? ABBC gives you AC. So this is why we can remove it, right? And you can check its equivalent. It goes both ways. You can remove it, you can add it. Okay. And finally, let's remove something here. Why can I remove the B in there? It's because A gives me B. So I don't need to have B in there because if I have A, I anyway have B, right? So this is why I can remove B. Who understands that I'm removing B in here? Okay, this is equivalent, right? Okay, so am I done? Am I done? I think I'm done. Yeah, that's it. That's the minimal basis, right? So it's a simplification and it's clean. It's not unique. If I give to several people the task of computing a minimal basis, they might have different results, right? So there's no unique minimal basis. It pretty much depends on the path of reasoning that you take, and you might get different results. Okay, here's another example that we can do together. Okay, so first we split, meaning that every time there are several attributes on the right, we use the splitting rule to split them like this, right? Just like this. This is equivalence, right? These are the 2 ways of doing it. So let's split it. Now we only have 1 attribute on the right. Next, we eliminate the trivial rules. Do I have any trivial rules in there? Well, with the reflexivity rule, I can find a few, right? Do you see the ABC gives you C? This one's trivial. If you know C, you know C, right? So you can remove it. What else is trivial? I marked them here in red. So A gives you A, we can get rid of. ABCD gives A, that's also trivial because A is on the left. ABCD gives you D is trivial because D is on the left, and AB gives you B is trivial. Who agrees? We can drop that? Okay, let's drop it. Okay, what next? Then we simplify the left-hand side. Can we remove stuff on the left? A, B, C. Well, if I know A, I know C, right? So I can remove C here in the second rule. I can get rid of C because A gives me C anyway. So if I know A and B, then I know A, B, and C. Okay. Next, what do I have? A, B, C, D. I can simplify things in there because if I know A, I know C, so I can remove the C in there, and I can remove the D as well because I have A and B already. I can remove C, I can remove D, right? Who agrees? Who gives me the authorization to do that? Okay, you have given me the authorization, so we do it. And here it's the same, C and D go away, right? So we simplify, and then we just keep going on and on and on and on and on again. We just iterate and keep doing the same thing all over again. So now, do we have any trivial rules? Or can we simplify things? So A, B, well, B gives me D, right, already. So A and B gives me D is useless, right? It's redundant. So I actually can drop that one. And I think we cannot do anything anymore. Does anybody see anything we can simplify? I don't think so, right? This is it, we are done. Okay, so we can say that now we simplified. So this is what we had on the right, gives us the left, but actually it's equivalent. It also goes the other way around, right? I draw the arrow in one direction, but it's really an equivalence, right? If you have the left, you can also reconstruct the right. But the one on the left is cleaner and simpler and tidier because we don't have these redundant rules. Do you see here that this is abstract because there are no relational tables anymore in here? We abstracted them away, they are gone, right? So we just work on these rules. This is exactly what mathematicians love doing, right? They write the axioms and they just use the axioms. It's a little bit like riding a bicycle and then you remove the little wheels, right? Then you just work on the axioms. Okay, who feels comfortable enough to compute minimal basis now? Okay, the closure I already know. You all succeeded in computing it, so now the minimal basis. Okay. Okay, you're doing well. So let's move on then. Let's move on to what we do with functional dependencies when we do projections, and you will understand why the projections are actually important. So imagine that I have a table with columns or attributes A, B, C, D, and then I project it. That's pi, right? Pi is for projection in the relational algebra. I used, by the way, I realized I used an uppercase pi, but it doesn't matter. I could have put in lowercase as well. So I project to A and B, right? So now I have A and B on the right. What do I do with the functional dependencies? Well, it's tempting to project them, right? So if you have A gives you B on the right, on the left, sorry, then you also have it on the right, obviously, right? Because it's a subset, right? You just project it. So you can take them over. Why don't I take over A gives me C? Well, that's because it wouldn't make sense. C doesn't even exist on the right. So this is why it goes away, right? So A gives me B. So it means that if I have a table and I have some functional dependencies and I project that table, then I can also project the functional dependencies to that new table, which will be a smaller set because some columns go away, but I can project them. Here there's a table, of course, but you can do the same reasoning on a universe of table, right? If you take a universe of table, then you project on some attributes, every table, you can also project accordingly the functional dependencies. Okay. Now, can anybody guess if I have A gives me C and C gives me B and A gives me B? Don't pay attention, by the way, to what's in the tables there. I just put random letters, but that's only variables. It's not actual content. So don't be confused if the functional dependencies don't match. I just put unique letters. So if I had on ABCD, the universe of tables with attribute ABCD, that A gives me C and C gives me B and A gives me B, what can I project to the right? Well, I can project that A gives me B, right? And by the way, A gives me B, I can get rid of with the minimal basis, right? It's actually redundant. But why did I put it in there? Because technically you project it. But now you can ask the question, okay, since A gives me B was redundant on the left, what happened if I had the minimal basis and I only had A gives C and C gives B? Then it would be tempted to say, okay, let's throw everything away then because C is there and you know they don't make sense. And then we end up with something empty on the right. But it's not that easy, right? You still have that A gives you B. So how does that work? Well, you need to take into account not just the functional dependencies that appear in your bag, but all of those that would be derived from them, right? So it's all of them. So one approach can be brute force. So that's just a repetition of what I said. It's all the functional dependencies that follow from the set, not just the ones that are in it, also the ones that follow from there with the actions, and that only involve attributes in the projection. So all those with A and B. So one way to go is brute force. You just try to infer everything. So how do you do that? Well, let's say we have A, B, C, D, and we have this set of functional dependencies on the left. And on the right, we project to A, B, C. So we drop D. How can I project the functional dependencies and determine the functional dependencies in A, B, C that would hold in the projection? Well, if we go brute force, really brute force, let's list all of the subsets. It's the power set, called the power set by mathematicians. So we take A, B, C, all possible subsets. So there's empty set, A, B, C, AB, AC, BC, and ABC. All right? Who's following? Okay. This is the power set. So technically, this is everything I could have on the left of a functional dependency, right? Because on the left, I have a set of attributes. Well, here I have all of them. It can never be anything else than that, right? What can I do now in order to derive the functional dependencies that exist from there? What can I compute with each one of these sets? Something you're good at. Starts with a C. You don't want to compute closures? Let's compute closures. You love doing that. Yes, exactly. I see somebody on Zoom. Congratulations. All right. So yes, you compute the closure. So I did it for you, right? You can see that A, the closure is ABD. You cannot derive C from A, no matter how hard you try. C, you can derive ABCD. AB, you can derive ABD, and so on and so on and so on. So since I know that you can compute closures because you got full score everybody to the closure assignment, I know that you can do that. And this is it. And what do we do next? Because that's a bit of a mess on the right. You only keep the projected attributes. So we drop D, and then we compute a minimal basis. We clean things up, right? But we need to clean up after removing D, because otherwise we might be back to square one, right? So I first drop D, and now I compute the minimal basis. Okay, what can I get rid of for the minimal basis? So that's another exercise for the minimal basis. Well, empty set gives me empty set, trivial. Let's throw it away. B gives me B, trivial, right? Goes away. Oh, I did one before, I removed A here. You agree, right? A gives you A, that's the reflexivity rule, can remove that. B gives me B, goes away. Then I can remove C here, right? Because it's already on the left, so I don't need to have it here. Then I remove AB gives me IB is trivial. AC gives me B, because A and C are already on the left, so this is also trivial because of the reflexivity rule. Then BC gives me ABC, I can just keep A, because BC gives me BC was trivial, and ABC gives ABC, goes away. Then I can split, you know, I kind of did it without splitting first, right? I can split next. So now I split CAB to CA and CB. Then what did I do here? I removed that AC gives me B, because that's redundant with A gives me B, right? I know that A gives me B, so AC gives me B is redundant, right? Who is following? Right? Okay. And then BC gives me A is also redundant because I already have that C gives me A, right? So BC gives me A is useless. All right. And C gives me B because of which rule? Come on, you know it. I'm sure you know it. On Zoom, maybe you're less shy. Yes, transitivity, exactly. So that goes away. So that's it. This here is the projected functional dependencies to ABC. So you see the idea, right? You take the power set of the attributes, compute the closure of every one of this power set. It's pretty brute force to do. Then you drop the columns that are not in the projection, and then you compute the minimal basis, and you're done. And you have the projected functional dependencies. Who is with me? Okay. Now, of course, the reason we are doing that, there's a reason, right, why we are doing that, because we want to achieve something. And you will see the pieces of the puzzle will very soon assemble. So now, I have this relation. This relation has functional dependencies, right? For example, oh, I didn't intend to talk first about the functional dependencies. I wanted first to project. So let me start with the projection. I'm going to project it in two ways. I'm going to project that to AB, and I'm going to project that to ACD. So I'm doing two projections, right? First, pi AB and pi. So here there's a duplicate, right? A1 was twice, so now I can remove it. That's because of the set semantics. And then I project to ACD, and I get this, and here I don't need to eliminate duplicates. Okay. So you can decompose a relation like that into two relations. The spirit here, remember the example I gave you with the anomalies at the start. We had this big table that had too many things, and we wanted to decompose it into smaller tables, right? So this is where I'm going here. I'm trying to find a way that we can take any table that has anomalies, and we would like to decompose it into tables in such a way that it doesn't have any anomalies anymore. So given a relation R and two sets of attributes that have to cover the entire, right? I have, if I take the two tables together, I have to cover all of the attributes. So I have A, B, C, and D. It's all in the projection. Then R, the relational table, can be decomposed into the two projections, right? But we need to do it wisely, because you cannot just go ahead and pick random columns and then project, right? That doesn't work, of course, as you can guess. You have to do it in a smart way, right? So this is why, for the smart way, I'm going to introduce another normal form to you. I wanted to just add a remark there, just so you're careful, but this is also a bit of brain gymnastics, that here A, B, C, D are the attributes. In this definition, A and B are sets of attributes, right? So just so that you're aware, but it's good to do a bit of gymnastics. Okay. Boyce-Codd normal form. Boyce and Codd are two of the main contributors to relational databases. Edgar Codd, you already know, and Raymond Boyce is another one. So they give their name, like the dream of any scientist, to something that people use, and that is the Boyce-Codd normal form. What is this? So let's look at the functional dependencies of this table. For example, A gives you B. You agree that A gives you B, right? Here. If you know A, then you also know B, right? If you know that A is small a, then B is 1. If you know that A is small b, then B is 2. Okay. C gives you D. You know that if C is true, then D is true. And if C is bar, then D is false, right? So we have this. AC, you could compute, also try to compute what's on the right. So that's the closure. What's the closure of AC? Well, it's everything, right? Because from A, you get B, and from C, you get D. So from A and C, you have A, B, C, D. What is AC? It's a super key, right? Why? Because it has everything. The closure, and a super key has its closure that is the entire set of attributes. It's another way of talking about super keys. So since I have ABCD on the right, the closure of AC is everything. So AC is a super key, right? I actually like that, to have super keys on the left of my functional dependencies. I actually like to have that. Here, I don't like that because that we have a functional dependency from A to B, but A is not a super key, right? The closure of A is not ABCD. If you try to figure out the closure of A, it's just A and B, right? You cannot add anything more. So you have a functional dependency here. A gives you B, where the left part is not a super key. I don't like that. This is exactly when the problems appear with the anomalies. I don't like functional dependencies such that the left is not a super key. All right, this is in fact the Boyce-Codd normal form. This is what I'm coming at. So in that case, right here, this table actually I like, because if I look for the functional dependencies, for example, I have AC that gives me D, right? You can see that it's true. How you can see it is that A and C are all unique, right? If you take jointly A and C, it's all unique pairs. So this gives you D and this gives you everything. So the closure of A and C is everything. So AC is a super key. This is a functional dependency I like. Actually, in that example, I don't think you are going to find functional dependencies that the left is not a super key. So this is a good table. All the functional dependencies you can find. Here are a few others. AC gives you D, AD gives you C, and CD gives you A. I actually on purpose built the table like that. But you can see that everything on the left, AC, AD, CD, these are all super keys. Who sees that these are super keys? Okay. So what happens here is that all the functional dependencies that I'm looking at are super keys. We say in that case that this relational table or the universe of relational table that has a set of functional dependencies like that is in Boyce-Codd normal form, right? Boyce-Codd normal form means everything on the left is a superkey. As soon as you have a functional dependency and what you have on the left is not a superkey, doesn't give you the entire table, then it breaks the Boyce-Codd normal form. Okay. Who is capable now of telling me if I give you, let's start maybe not directly a table, but a set of functional dependencies, who can tell me easily if it's a Boyce-Codd normal form now? So let me give you the algorithm again so that it's crystal clear. If I give you a set of functional dependencies, you want everything on the left to be a superkey. How do you know it's a superkey? The closure must be everything. So what do? You take the functional dependencies, look on the left, and compute the closure of everything. This is what you love doing and you're good at it. So you compute the closure of every single set of attributes on the left, and you check that every time, bingo, you get everything. Then it's the Boyce-Codd normal form. Who can do it now? Okay, awesome. So this is it. Okay. So I don't like dependencies where what I have on the left is not a superkey. But of course, you need to be reasonable, right? Because of course, you can make up some trivial rules. Like, for example, I could say A gives me A, but A is not a superkey, right? But A gives me A is a trivial one. So of course, when I say I don't want non-superkeys on the left, I only mean with non-trivial dependencies, right? So I ignore the trivial dependencies. So AC gives me A, for example, is totally irrelevant. Okay, now we can work with small theorems or, things that we can figure out. For example, something that's actually quite cool and it's actually quite intuitive is that if I give you a table with just 2 attributes or a universe of table with just 2 attributes, it is always in Boyce-Codd normal form. You don't even need to check. Right? If I tell you there's 2 attributes, it's in Boyce-Codd normal form, period. So now let's show it. It's something that you can do actually looking at all the cases. There's the case that the only superkey is AB. There's the case that the superkeys are A and AB. So you have the functional dependency A gives you B. Then you have the case on the bottom left that B gives you A. So the superkeys are B and AB. And then you have the case that both A and B are superkeys. Let me remove that bottom toolbar of Zoom for the lecture hall. Oh, need to not touch anything once. There you go. So this last one right here, you see that A and B are superkeys. So you can check all of these are in Boyce-Codd normal form. How do I know it? Well, here, if you look at the functional dependencies, the only, you really don't have any really. Here, you cannot have non-trivial functional dependencies. The only superkey is AB, right? So technically, you have AB gives you AB, but that again is trivial. So since you don't even have any functional dependencies, then it's in Boyce-Codd normal form. Here, the only functional dependency you have that is non-trivial is A gives you B. Is A a superkey? Yes, A is a superkey. The closure of A is AB. So A is a superkey. That's in Boyce-Codd normal form. This one, the only functional dependency that is non-trivial that I have is B gives me A. B is a superkey because the closure of B is BA. That's everything. So B is a superkey. So that's fine. That's in Boyce-Codd normal form too. What about this one? When here I have 2 non-trivial functional dependencies, A gives me B and B gives me A. Is A a superkey? Yes, because the closure of A is AB. Is B a superkey? Yes, because the closure of B is BA. Every time you get everything. So the closure of everything on the left here is always everything. So this is also in Boyce-Codd normal form. So these are really, if you think, the 4 possible cases, there cannot be any other case. We covered them all. So you see, in this case, this case, this case, and this case, we always have a Boyce-Codd normal form. Who agrees? Okay, so this is easy, right? If you have 2 attributes only, then you are in Boyce-Codd normal form. You cannot have any anomalies. So we are trying to build our nice schema with several tables, right? To be with everything in Boyce-Codd normal form. That's our goal. But we have to do it wisely, this decomposition. We would like the projections to be in Boyce-Codd normal form, if the original table wasn't. But we also want something equivalent, right? If I go the other way around, so I project. The other way around is that I reconstruct the original table. How can I reconstruct the original table from the two projections with a zoom? Yes, yes, I heard it. A join, exactly. You join them back. And then the question is, if you join them back, do you get back exactly the table, right? That's our wish list. This is what we'd like to have. Okay, now you can try to be smart and say, okay, but wait. We need to project this table into plenty of tables that are all in Boyce-Codd normal form. What about just projecting everything to tables with two attributes? Done. It's all in Boyce-Codd normal form, right? It looks like a good idea on paper to do it that way because this is all in Boyce-Codd normal form. The problem with that is that the reconstruction doesn't work. You can try to join them back. You will not get the original table. In fact, you will get too many tuples, more than desired. Okay, so you need to choose your projection wisely. So the way you choose your projection is you look at the functional dependencies. You look at the left, are they all super keys? If they are all super keys, then we are done. That's it. That's a Boyce-Codd normal form. We don't have to do anything. If it's not in Boyce-Codd normal form, then it means that somewhere in my functional dependencies, one of them breaks the rule. One of them has something on the left that's not a super key. So you pick this one, so one that breaks the Boyce-Codd normal form. For example, A gives you D here. That's just to show you if I change the data. Here I have that A gives me D. Do you agree that A gives you D? Right? If A is small a, then D is true. If A is small b, then D is false, right? If I had here, if I change the value right here, I changed it, right? If I change this value to foo, then I also get that A gives me C, right? Then I have A gives me C, A, D. But let's get back to that case with bar. So A gives me D. I don't like these functional dependencies. I don't like it because A is not a super key, right? If I give you A, you might know D, but you don't know B and C. So this breaks the Boyce normal form. So you get into anomaly issues. So we're going to focus on that functional dependency that I don't like, and we're going to use this functional dependency in order to decompose. So AD, everything on both sides gives me one projection, right? So this is projection one, A and D is one table. In the other projection, I have the left A, but then with everything else, right? So that's B and C, that would be the ones that are not determined by A. So what's important here is that A, which is the left that is not a super key, this A is my joining criterion, sort of. So A is going to be in both of the projection, on both sides. This is how you join back. And the rest is one side has D, one side has B and C, but A is always there.
A question from two. So yeah, why do we assume that A gives D and not D gives A?
Well, you can. You just pick one. Here, I took an example of a functional dependency that A is not a super key. You could pick B gives A. B gives A is true, but do you see why B gives A does not help me here? Can anybody tell me why we cannot use B gives A for the decomposition? What's the problem with B? I'm helping you. All the values are unique in column B. What can you infer? B is a super key. So B gives me A.
From Zoom.
Yeah, go ahead.
Yeah. B is a super key.
Yes, exactly. So B is the super key. And as a consequence, the functional dependency B gives me A is totally fine with me. I like it. I like it because I have something that's a super key on the left. So this one is not problematic. This is why we are not going to use it for a projection. For my projections, I need to find a functional dependency that breaks the rule. I need to find a functional dependency that I do not like, right? In that case, A gives me D. Does it answer your question? Was it on Zoom? I can't remember who asked the question. That was on Zoom, right? So did I answer your question? I'm going to assume that I did. Yeah, okay, no worries. Oh, sorry, I misunderstood you. You didn't mean B gives you A, you meant D gives you A. And yes, yeah, absolutely. Yeah, I agree with you. I could have taken D gives you A, right? Because D is not a super key either, right? So D gives me A could have been as well. So you see, there's not only one way to do that, right? You might have multiple functional dependencies that break the Boyce-Codd rule, so that would work as well. You can try to do it as an exercise, actually, if you want, to use D gives A instead of A gives D, then you're going to get a different decomposition. Very good question, very good observation. Thank you very much. Okay, so the left, that is not a super key, is going to be on both projections, and then the rest is partitions, right? BC on one side, D on the other side. This is what I get. This is my decomposition, right? Now you see why I'm doing things like that, right? Because now, since A gives me D, now on the left, A is the super key now. Do you see? I still have A gives me D, but since I got rid of B and C, now A is a super key, right? So now I have Boyce-Codd on the left, in that case, and on the right, I don't know. You know, maybe you need to do it recursively, right? Either they are both in Boyce-Codd normal form, or they not, but then you decompose again and again and again and again, right? If you take the example we had last time, I had to do 2 iterations because we got 3 tables for one with the products and sales and customers, right? So you just iterate and iterate and iterate until you get only tables that are in Boyce-Codd normal form. What you need to be careful about is that when you decompose, you always, always, always must identify functional dependency that breaks the rule, where the left is not a super key. Then you decompose it that way. Who would be able to decompose like that? Tables? Okay, majority. Okay. So, and then this actually is something that you answered brilliantly. Indeed, the goal, the reason why we do that is that we want to reconstruct. It's the same thing that we already did with the 3 tables, product, customers, and sales in the anomaly example. You want to join back. You join on technically foreign keys and primary keys, right? So technically on the left, A is a primary key, right? Now it's a super key, it's also a candidate key. You can check and you can take it as a primary key. And on the right, A is a foreign key, right? So it points back to the other side. So you can join the foreign key with the primary key, right? So you join and you get something that might or might not be the original table. Sometimes you're lucky, it is the original table, then you have a perfect decomposition. Sometimes you're not lucky, you might get a join that actually gives you too many tuples and you lost information. So here you need to think about it. Why am I saying that getting more tuples means losing information? You can think about it offline. You are actually losing information. Imagine, just to make you think, imagine that I add so many tuples that I add virtually every possible tuple I could possibly have in my table. In a table like that, there is 0 information, 0 entropy, because that's just the Cartesian product of all the domains, right? So if you have too many tuples, then you lose information. Okay, turns out that some smart person invented an algorithm that can tell you whether or not the join gives you back the original table. I'm just going to check the time. 2 minutes. Oh, then I'm going to give you the break now. I think you deserved it, right? Because you followed everything that I've been explaining to you. So I'm going to save the chase algorithm for after the break. Then I explain to you how you check that by joining back, you get the original table or not. And then we'll wrap up with database design theory. And I might even be able to start on the next series of slides. All right. Thank you for being so awesome. And I'll see you in 15 minutes plus 2 minutes, so 17 minutes at 11:15.